don't know when they changed the fire alarm sound to be more like an air raid siren, but like my heart rate is still coming back down, so I'm half tempted to start today's class with like meditation and breathing exercises or something for this minute, 24 hours to say the least. So here we go. Okay. Well, hopefully they're not like cycling through the whole engineering quad and going to do this building next, because that would just make my day at this point. But, all right. All right, a couple announcements at the beginning, and then today we are going to talk about, as promised, pulse width modulation. All right. Fire alarms are exciting. Okay. Miscellaneous announcements before we dive into the PWM stuff. Okay. Good news. This class is not federally funded, so if you've been reading the news for the last 24 hours, you all still get your $40 for the robot project.
No internship, but
maybe, yeah, please. So this doesn't affect me as a lecturer. I don't run a research lab, but like if you're waiting for an email from a professor, give it a few days maybe, because I think a lot of people are going to be scrambling to figure stuff out at the moment. And I realize, I haven't talked about politics or global events much in class this semester, in part because as a visiting lecturer it's kind of above my pay grade to address a lot of that stuff, also in part because I like to just try and control what I can, which is this class, and creating a supportive environment and keeping things orderly in here when many times it feels like the rest of the world is either literally or figuratively on fire. So I realize it may be hard for some of you to concentrate for various reasons, like if you have parents who work for the federal government and just got laid off, or know people at risk of being deported, or again, there's like a war or something else going on in your home country, or a wildfire in your hometown, or like generally a lot of crap going on at the moment, right? So again, acknowledging that like, I don't want you to think I seem oblivious to all of that, I'm aware of it, I'm just, maybe it's nice to come just think about resistors for 50 minutes 3 times a week and kind of be able to forget everything else that is going on outside of this room. I don't know. It's a welcome distraction for me sometimes as well. Okay. Speaking of the robot, last time we kind of wrote those functions for making it steer at full speed. I mentioned how many of the motors are kind of janky from years of being abused by students and do not spin at the same speed. So if you want to straighten your robot out, or if you want to, say, do a gradual turn maneuver instead of just pivoting in place, you need to control the motor speed. So that's what we're going to do today. We have, I believe at some point earlier in the semester, I forget when, talked about pulse width modulation, or PWM, where the Arduino's pins are digital outputs, right? So they can either be high or low, they can't be in between. They can't be 2.5 volts. Okay, so if you want to control the speed of a motor, you basically do that by varying what's called the duty cycle of a square wave, or the percentage of time that it's high. Okay, so if we have a line that's just flat or low all the time, that's a 0% duty cycle. Okay, if it is high 25% of the time and low 75% of the time, so on, that's a 25% duty cycle. If it's on half the time, off half the time, it's 50% duty cycle. I'm not going to draw, or I guess I'll just draw a bunch of them. If it's on 75% of the time, you get the idea. That's 75%, all the way up to just being high all the time. It's a 100% duty cycle. Okay? So, and as you should have seen in Lab 3, there's kind of roughly a correlation between this duty cycle and the motor's speed. At very low duty cycle, the motor might not spin at all because there's some internal friction it has to overcome. So if you just hear kind of like a high-pitched whining noise and the motor isn't actually spinning, that's probably why. You need enough of a duty cycle to kind of overcome that friction and get going, but rough correlation, linear correlation with motor speed, maybe not perfect. Okay, cool. So to control the speed of a motor, we need to generate a square wave like that. In Lab 3, you did it with a function generator. Now we want to do it with an Arduino. Okay, so how do we do that with an Arduino? First thing that might come to mind is just using delays, right? So just kind of writing out pseudocode here. Turn a pin high, delay, set the pin low, another delay, and just alternate doing that in the loop, right? So set up in high, wait for a certain amount of time, set up in low, wait for a certain amount of time, and so on. And then to change the duty cycle, I would change those two delays. All right. Technically that would work, but that is going to get really messy if you want multiple PWM signals. So imagine if I was doing more than one of these and I have, okay, I want this one at 50% duty cycle and this one at 25% duty cycle. I didn't even draw that right, but this one at 25% duty cycle. So now I have to kind of figure out what are all these different delays and when am I setting each pin high or low. And now your program is going to be hung up in the delays, which we've learned you can get out of with an interrupt, right? But ideally you don't want your whole main loop just filled up with delays generating a PWM signal. Okay? So that's kind of one method. Another easy method would be to use an Arduino function for it called analog write, where you tell it the pin number and the value, which is, this is an 8-bit value from 0 to 255, corresponding to 0 to 100% duty cycle. So if I tell it analog write 3, 255, that would tell it to send a 100% duty cycle signal to pin 3. If I want to figure out 50%, then that would be about 127 or 128, right? So it's 0 to 255, not 0 to 100. But you're not allowed to do that in this class, right? We're making you do the hard way, do this the hard way with registers and not using Arduino libraries. So we don't want to use delays. We can't use the analog write command. How are we going to do it? What have we learned about that kind of keeps track of time so far? Somebody say it. Timers, yay. We are going to do this the hard way with timers, kind of what the analog write function is doing in the background. So review of what we've done with timers so far. Okay, so we're going to look at, there are 3 timers on the ATmega 328P. We have timer 0, which is 8-bit. That means it counts from 0 to 255. We have timer 1, which is 16-bit, which counts from 0 up to 65,535. And then we have timer 2, which is also 8-bit, so it counts from 0 to 255. You are probably going to be using this one for your color sensor. And if you decide to use one for the ultrasonic sensor. Okay, that 16 bits means it has a much higher resolution. It can measure tinier chunks of time. So it's a lot more accurate when dealing with measuring the length of those pulses coming out of either the color sensor or the ultrasonic sensor. That is not to say you have to. If you decide that you want to generate a more accurate PWM signal with finer resolution, you could also do that with timer 1. Okay, this is just me. So this is me kind of steering you in a direction that might make the most sense, assuming your robot's using one or both of those sensors. But again, you don't have to do this. Okay, so today we are going to be using everything we are going to do today. I'm going to be using timer 2 as an example, but it also applies to timer 0, which is 8-bit. Okay, the difference is that timer 0 is going to have different names for the registers that control it, so you need to go look up those registers in the data sheet instead of the registers for timer 2. Okay? Pardon me. And I am going to squeeze this on the bottom here instead of starting a new sheet of paper. So far, we looked at 2 different modes of operation for these timers. We had normal mode, where an 8-bit timer counts up to 255 and then overflows, right? It can't count to 256. Okay, so just if you turn it on in normal mode, it's just like a stopwatch that runs up until it runs out of digits and wraps around back to 0. Okay? And what you did with that in the lab was, okay, we're going to start the timer, and then we're going to grab the timer value when some external event is triggered, like a pin change interrupt, and then we can tell how much elapsed time there was. With Again, the caveat that for all these timers, we have that, I forgot to mention this, 62.5 nanosecond clock tick at 16 megahertz. So these numbers are all for clock ticks, not seconds. So you always need to multiply these by that 62.5 nanoseconds to convert to actual units of time. Okay? We also saw CTC, or clear timer on compare mode, where again there's that max value of 255, but now we pick some separate output compare value, which is between 0 and 255. The timer only counts up to that and then it resets, so it doesn't go all the way to 255. And then each time that happens, it generates an interrupt. So that was how we said, okay, if we want to do something like blink an LED on and off once a second, that's how we can do it with interrupts and without using delays. Okay? That should all be review of what we did with timers kind of before break, which I realize might have just fallen out of everyone's brains by now. So, questions or clarifications on how timers work before we move on to using them to generate PWM signals? See a bunch of people still writing, so if I went a little too fast there, I'll wait a minute. 0 questions? Everyone's good conceptually with timers? As always, I don't believe you, but okay. We'll again let people catch up on the writing. All right. So we are going to need a whole sheet of paper for this part. We are going to now look at a new timer mode. PWM mode. Technically, there are multiple different PWM modes in the datasheet. This one is called, which we'll talk about a little more when we look at the datasheet, this one is called phase correct PWM. And we're not going to dive too much into the different types in the datasheet, so don't worry too much about what that means. So now, here's what the timer is going to do. Okay, so we have our graph set up with 0 to 255. The timer is going to count up, but instead of overflowing, it's then going to count back down. And then when it gets back to 0, it's going to count back up. So it's going to generate kind of this triangle wave. Okay. And we are still going to pick this output compare value. Okay, but the timer's not resetting when it hits that value. So it's not like clear timer on compare mode. It's just going through that value and still counting all the way up to 255. Okay? But something is going to happen when those two values cross. Okay, so when the timer is counting up, it crosses that value twice on each cycle. Once when it's counting up, and once when it's counting back down. The microcontroller is going to toggle the voltage on a pin that we select when that happens. But it is going to kind of do this in the background without requiring any active code. Okay, so once we've set this up initially, it's just going to do that automatically, and we don't have to think about it anymore in our code. There's no delays turning pins high or low. So if we look at each point where this intersects, kind of draw vertical lines here showing all of those intersections. Okay, so it's going to take some to draw. Okay, so if this pin voltage, so this is going to be toggling between 0 and 5 volts. This is actually representing the physical voltage on our Arduino pin. This one's not a register. It's not going to 255. Okay, so if that starts low, like this, okay, then this cross happens. Okay, that voltage is going to go high. It's going to stay high until this happens again when those intersect. Now it's going to go low. You can probably guess how the rest of this is going to get filled out. And each one of those intersections is going to toggle. Okay, so I am generating what we set out to generate, a PWM signal, based on this. I have the counter doing a triangle wave, and then I'm just looking at where the counter intersects that output compare value. Okay, now that's one way to do it. This is called set on up counting, because meaning when the timer is counting up, so when it crosses that threshold on the way up, then I set this voltage high. Okay, and we can also do that the opposite way. So again, this graph is pin voltage. And draw these all down. And where if this voltage is high initially, then it goes low when this intersection happens. Okay, so it's high, goes low, goes high, goes low, and so on. Okay? And that one is called clear on up counting. So when the timer is counting up and that intersection happens, we clear or set this voltage to 0. Okay, now, let's try and zoom out a little bit so I can see all three of these better. Now look what happens if I change this output compare value. So say if I make that output compare value higher, like up here, this is where it's going to get a little messy, but I'll kind of do my best to keep this diagram clean. I'm actually just going to do it, well, and draw these down, right, our new intersections. Okay, so now, in this case, my duty cycle got lower, right? I'm now not going to go high until it gets there, and then I'm going to go low again sooner. Stay low for longer. Go high. Stay low for longer. Okay, so this would be easier if I had like a video or something animating this, but can you kind of visualize how if I move that output compare line up or down, that makes this pulse get wider or shorter, right? I'm not changing the frequency, okay? The frequency of that triangle wave is still the same. So the frequency or the period of the square wave is still the same, but moving the output compare value up and down changes the duty cycle, okay? And then if I look at that for this one, same thing, I'm going to extend these lines down. Okay, same thing. Now, if I move that output compare value up, that's going to increase the duty cycle instead of decreasing it. Okay, so that makes it go high for longer. Okay? Of these two, I find the low, so both of these are perfectly valid and will work. I find this one more intuitive because for here, a 0 to 255 output compare value is going to correspond to a 0 to 100% duty cycle, right? So if I move my output compare value all the way up to the top up there, then this is just going to shrink down to 0 and this will be high all the time, right? If I move it all the way down to 0, this is going to, the negative part of the pulse is going to keep expanding and this will be low all the time. So that relationship is more intuitive to me, right? Increasing your output compare value means you're increasing your duty cycle. Here that's inverted. If you make the output compare value, so if the output compare is 0 to 255, then that corresponds to 100 to 0% duty cycle, so the mapping is inverted. Either one works in your code. If for some reason you think that first method makes more sense, fine, but this is how the Arduino analog write function I mentioned works, right? When you send it 255, it's going to go full speed. When you send it 0, it's going to be off. Okay? So that is all without touching any registers, just kind of conceptually showing what the timer is doing and how the PWM signal is generated as a result of it. Okay? Questions on that? Nothing? Okay. We're going to, again, try to get to Tinkercad today, but we'll see how far we get. All right, to set that up, remember our timer control registers that we used for other stuff with timers. And I'm going to jot them down here rather than scrolling back and forth through a bunch of different pages of the datasheet. For timer 2, we're going to have TCCR2A. Remember, for timer 1, it was TCCR1A, right, which is going to have 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. COM2A1, COM2A0, COM2B1, COM2B0, 2 empty bits with no names, WGM21, WGM20. So these are our waveform generation mode bits, which we used before. Remember, when we weren't using a PWM mode, I told you to kind of ignore these COM bits, so we're going to need to deal with those today. And then we have TCCR2B, which is going to have FOC2A, FOC2B, 2 blank bits, that third WGM bit, WGM22, and then our clock select bits for the prescaler again, CS22, CS21, and CS20. Okay, so to set up a PWM mode, just like we set up when you set the timer up in normal mode or you set the timer up in clear timer on compare mode, you have to figure out what all of these bits need to be. Okay, and I'm going to tell you now that the blank ones are just 0. Okay, and we're not worried about this force output compare bits. We're not using them in this class. What I'm going to want you guys to do now, though, is fill in. I'm going to need to pull up the pinout thing and data sheets. So sorry, I forgot to have those open in advance. I'm going to want you to practice looking in the data sheet to fill these up rather than me just writing them down for you. So I'm going to leave that up for a minute because I realize people are still writing. All right, I'm going to switch over to the laptop. And it would help if I plug the HDMI cable in. All right, so pinout diagram, which I haven't talked about yet. The Arduino has, if you've ever looked closely, 6 pins with this little squiggly line next to it, right? Only certain pins can generate PWM signals. Okay? This is a kind of hardware functionality built into the microcontroller that is only available on certain pins. So we see we've got pins 3, 5, 6, 9, 10, and 11 that have the PWM signal. We have 3 timers. Each one is linked to 2 pins. So you can tell which timer is connected to a specific pin by looking at this giant blob of acronyms over here. So I have OC2B, for example, here on pin 3. That means pin 3 is connected to timer 2 output compare B. Okay, somewhere on here, up, they're not in order, OC2A is up there. Okay, so pins 3 and 11 are linked to timer 2 PWM. Pins 9 and 10, OC1A and OC1B. Okay, our timer 1 PWM, and then timer 0 is on here somewhere too. There's 0A, and I think this diagram might actually be missing the label for 0B, but it's on there somewhere. I think in the part up that shows the direct connections to the microcontroller as opposed to the Arduino breakout, it's up there. Okay, 6 PWM pins, 3 timers, 2 pins per timer. You have to look to see which pin you want to use, which timer it corresponds to. Okay. Looking at now the data sheet, Okay? Starting on datasheet page, roughly, I don't know why it's freaking out like that, there we go. 203, we have timer 2, control register A. Okay, we're similar to, we've seen these tables before. We have a table for the waveform generation mode bits. Right, where so far we've seen normal mode and clear timer on compare mode. Now we have a bunch of different PWM modes. Again, there's phase correct PWM and fast PWM, and there's actually 2 of each, which are slightly different according to the rows in this table. So I'm going to tell you now, for today, we want to use mode 1, the phase correct PWM. Okay, so I'm going to jot that down here. Which I'll switch back to the document camera so we have this. Okay. And if we keep going, we're going to have a clock select bit table, again, where some weird bug in the data sheet, that empty cell should be a 0 there. Okay, but there are different values we can select here to select different prescalers. This one is interesting when we get to talking about motors. So this is not controlling the duty cycle of the PWM signal. This is going to control the frequency. Okay, so increasing the prescaler is going to spread out that whole triangle wave, give it a longer period, and decrease the frequency. So this is something you will need to play with to see what gets the best response out of your motor. Okay, if that prescaler is too big, especially for timer 1, then remember, for the max prescaler for timer 1, it takes something like 4 seconds to wrap around, right? So a couple seconds is enough time for your motor to ramp up to full speed and then stop again, right? So if we talked about duty cycle corresponding to speed, but if your duty cycle is too low, then rather having it look like the motor's going at constant speed, you're actually going to see the motor ramp up and ramp back down. Just like with lights, right? Like if you use PWM to dim a light, the frequency of that signal needs to be faster than the human eye can see, so it just appears dimmer. If that frequency is too low, then you're actually going to see the light toggling on and off. Okay? On the other end of the spectrum, if that frequency is too high, then your motor sort of acts like a low-pass filter, right? If that frequency is really, really fast, then the motor actually never has time to build up any speed, because the voltage, remember our RC time constants from earlier in this semester, right? If you have enough time, then the speed will ramp up, but if you don't give it enough time before you go low again, then the speed just kind of bounces around near 0 and never ramps up. So point being, for purposes of today, we're just going to set the prescaler to 1 with the CS bits. I'm going to jot that down again before I switch back to the document cam. But you will need to find the value that works best for your motor and actually gives it the maximum speed. Okay? And then the bits we haven't talked about yet. Now there's a bunch of different tables up here, so these COM bits. And if you look at these tables, it'll tell you values for the COM bits, but you have to be careful to look at the table header because there's different tables for different modes. So this one is for the non-PWM mode, that's not what we want. This one is for fast PWM, that's not what we're using. These are for phase correct PWM, that is what we're using, but these are for COM2A. We're going to do this demo for pin 3, which was COM2B, or output compare to B. Okay, so we need to keep going. Here we have that B, non-PWM, fast PWM. There we go, finally, that table. Phase correct PWM mode. Okay, we have values for these bits that say normal port operation OC2B disconnected. That means even if you set up the other registers otherwise, it's not actually going to generate the PWM signal on the pin. Reserved, this means it kind of does nothing. And then here are those 2 phrases I mentioned earlier. Clear OC2B on compare match when up counting. So that means when the timer's counting up, it's going to set the pin voltage low. Set OC2B on compare match when up counting. That means when the timer's counting up, it's going to set the pin voltage high. Okay, so those bits, COM2B1 and COM2B0, are the ones you set to choose which one of those modes you're in. So I'm going to jot that down here again. Clear OC2. Okay, now you, if you don't already, are going to want to pull out your laptops and pull up the data sheet. I'm going to switch back to the document camera. Rather than just giving you the values here, I want you to do the 3 things we just discussed. So again, I'm going to tell you now, we're not using the pin corresponding to output compare A. So those 2 are also 0. But you need to look up in the datasheet, because I want you to practice doing this, because everybody's robots are going to be different. You're going to have things assigned to different pins, so you might not be able to just copy and paste all the lecture example code. So I know this is painful, but again, I don't just want to jot this down for you. I want you to look up the information in all those tables. So starting around page 203 in the datasheet, look up and fill in the values for the timer to do this. You want to set the WGM bits to mode 1, phase correct PWM. The clock select bits, set the prescaler to 1, but again, if you do this with a robot, we need to test prescaler values for motor. From what I remember, if the prescaler is 1, that's actually, again, on the end of the spectrum where the frequency is too high and the motor won't actually spin. I think when I remember testing this a few years ago, I wound up having to set the prescaler to 256, but do not quote me on that. Okay. And then the COM bits, again, we want to clear OC2B on up counting. Okay? Look up all and fill in all the values to do that, because we are going to need them in the Tinkercad code that we might barely get started on at the end of today, and then if not, we'll continue on Friday. Okay? Yeah, I realized maybe I went kind of fast there. So any questions on the datasheet stuff, how the PWM mode works? Yeah. Yes. CA, I don't know why that says CA instead of CS. No, it's just a weird typo in the datasheet. So if you scroll back up to the register. Yeah, it says CS there. I think that, okay. So there's a weird, again, sometimes there are weird typos in the data sheet where the table calls them CA instead of CS bits, but I am not, like, those values are still right. So I don't know why it says CA instead of, yeah, because there's CS20. Yeah, okay. I don't know why it says CA22 and CA21. Yeah. Okay, I'm going to switch back to the document to the laptop for a moment and kind of walk you through some of this. Okay, so again, to help if I turn my mic back on. Clear on upcounting. So for clear on upcounting, you're going to want COM2B1 and COM2B0 to be 1, 0. Okay, so if you look at the corresponding register, that means you would have a 1 and a 0 here. Okay, for phase correct PWM mode, your WGM bits are 0, 0, 1. But remember, those bits are somewhat annoyingly split across the 2 registers, right? So WGM 22 is in this one, so that bit is 0, and these two are then 0, 1. And then for the prescaler or clock select bits, and for if those are all 0, then the timer's not doing anything. So even if you've selected a PWM mode with the WGM bits, if you forget to set the clock select bits, then the timer still doesn't do anything, right? It's just off. And again, there's this weird blank cell there that should be a 0 for some reason, so those need to be 0, 0, 1 to turn it on, set a prescaler to 1. Okay, so switching back to the document cam and filling all of those in. This is 0, 0, 1, 0, 0, 0, 0, 1, and then 4 zeros, another 0, 0, 0, 1. Okay, all of that is doing this. Just think of these kind of your controls or on-off switches for the different timer modes. Okay. Questions or any confusion on? Yes.
Why did you use 2 zeros on COM2A1 and 2A0?
Because, so why did I use 2 zeros on COM2A1 and 2A0? Because we are using, let me switch back to the laptop. So I should have written down, actually, all of this is for assuming we are going to use pin 3. So when we get to the Tinkercad part, this is the pin we're going to be using, and that, so this says output compare to B. So each timer has 2 of these, A and B. We are using the one corresponding to B. So there is also pin 11 is OC2A. So if we go back to the data sheets, these 2 bits here, COM2A1 and COM2A0, are for pin A, and these 2 are for pin B. So if, for your robot, if you wanted to control the speed of both motors, you would use both of those pins, and then you would also choose something for the COM2A bits, but for this demo, we're only doing it with B, so we're just leaving those as 0.
So it's just B3s and 3s.
Yeah, it's because we're only doing this with 1 pin, okay? But you would go through the same, so you don't, and I guess this is important to clarify, so the waveform generation mode bits and the clock select bits are for both pins, right? But then these 2, it would be, if for some reason you wanted to set, like, have one of them set on up counting and one of them set on down counting, you could select 2 different modes for the 2 different pins, but you can also just set them both to the same mode, which again I think is more intuitive, because then you would have both motors evaluated as 0 to 255 would control the speed of each motor, but you would have 2 different variables for that, which is what we are barely going to hopefully squeezing in with Tinkercad here, because people already have their laptops in. Okay? Other questions on the datasheet stuff? Okay, and I know we only have 5 minutes left, but I posted, I think I did it right this time, posted a Canvas announcement with a link to a starter circuit, which again just has an LED wired already, so we don't have to waste time wiring stuff. So please go ahead and pull that up with the remaining time. We'll see how far we get and pick up on Friday. So really important note, as of today, and I think I mentioned before, Tinkercad is a client-side simulation running in your web browser, not on their server when it actually runs the code, meaning it's not properly emulating timer stuff perfectly. So a lot of code with timers will not actually work when you simulate it. So we are going to set this up to be the equivalent of what the analog write function would do dimming an LED. I'm actually going to show that real quick. So analog write does work in Tinkercad, but kind of doing it manually with registers does not. So if I start this simulation and open my serial monitor, I'm going to zoom in on the LED. You can see it's not perfect, but I have a value over there ramping up from 0 to 255 and then back down, and it's kind of fading the brightness of the LED on and off. Again, not perfectly, but you kind of get the idea. The same concept applies to controlling the speed of a motor. Okay, so this wire would be going to one of your H-bridge inputs instead of to an LED, but the code would be the same. Okay, so this runs in Tinkercad. When we set it up with registers, it will not run in Tinkercad, but it will work on a physical Arduino. Okay, so we'll still be doing it in Tinkercad, since programming the physical Arduinos in a lecture hall is kind of a pain. And I'll leave the big comment at the top that says, again, in all caps, do this in your version too. Warning, this will not work in Tinkercad. Okay? I actually just remembered, let me see, that the wall clock is running slow, but we still have 2 minutes left. So, open up that starter circuit. Again, important, put this comment in your code. This will not work in Tinkercad. First thing to note that I haven't mentioned yet, for all of this, you also still need to set the pin as an output. Okay, so even though we were talking about timer control registers, you need that data direction register to set whatever pin we're using as an output. So in this case, that's pin 3, so I could do 1, left shift 3, or again, write out all the 1s and 0s. So set that pin as an output, which we're going to be using for PWM later. Okay? Set pin 3 as outputs. And then what we're going to be doing, but are going to run out of time to do, is type in those values we already chose for the timer control registers, so TCCR2A and TCCR2B. Okay, and then next time I will show you, once we've set everything up, okay, how do you actually change the register value that's going to change the duty cycle of the PWM signal, which you can use to control the speed of the motor. But we're out of time to do that today, okay? So we will leave it here and pick up on Friday. Hopefully we get through the rest of the day with no fire alarms, and as usual, I will be around for questions, okay? Thank you.